So again, thank you all for joining today. My name is Jennifer Shacken. I'm with New England Forestry Foundation, and our organization has been a member of the Climate Smart Wood Group Steering Committee for a number of years now. And so we're really excited to bring you the first in a series of webinars today. I'm going to be providing us a little bit of an introduction to get us started before we go to our speakers. First, the Climate Smart Wood Group came together to help the building sector in North America procure climate smart wood products. And it's really built on the premise that interest in better wood can create market incentives that improve the way forests are managed and help fulfill the full potential of forests as a natural climate solution. And the organizations that you see listed here are represented on the steering committee of the Climate Smart Wood Group. It's currently a volunteer-driven effort. And so if you'd like to get involved or ask a question, you can certainly do so by using the email that you see on the screen there, info@climatesmartwood.net. But of course, please keep that in mind when you reach out, that it's a bunch of volunteers behind the scenes who just care about these issues a lot. And we have to give a huge thank you to our sponsors, which include Lowe's, Timber Lab, and Columbia Forest Products. These sponsors and their support are making it possible to provide the Climate Smart Wood Group website, all the resources that are located there. There's an updated guide to climate smart wood procurement that's also on the website, and this webinar series. So once again, a huge thank you to these supporters. And for you all, there are a number of different ways to get involved in this effort and support the work if that's of interest to you, including donating. There's a button right on the website. It's pretty easy to do. Becoming a sponsor and joining the folks that you saw on the previous slide, and participating in the webinars like you're doing today, sharing the information within your network, and then actually using that procurement guide. I will put a link to that in the chat in a moment so you can find it. It's an easily downloadable PDF available now. It's recently been updated. This is the first in a monthly series of webinars we'll be doing over the course of 2026. Our speakers today are Jason Grant with World Wildlife Fund and Seth Zuckerman with Northwest Natural Research Group. As you may have noticed earlier, both also members of the Climate Smart Group Steering Committee. I'll let them introduce themselves shortly. But one last note before we begin is that we have the Q&A function enabled for this webinar. So please feel free to submit questions at any time throughout the presentation. Everyone will be able to see the questions that are submitted, and you can actually upvote questions if you really like that one and you want to hear the answer. We will aim to be wrapping the presentations about 15 minutes before the end of the hour, and then at that point, we'll have a chance to field some of those questions. We might not get to all of them, but you should feel free to reach out to the speakers directly, or we'll try to follow up after the fact. And with that, I will turn it over to Jason.
Thanks, Jen. Do you want to do a poll? Do we have a poll, or does
I
that
think
come later?
we'll wait. We'll wait and right before
We'll
Seth's
wait on the
presentation.
poll. Okay. All right. Great.
Sneak preview, everyone.
Thanks. Yeah. Sneak peek. All right. Thanks a lot. Let me share screen here. And sorry for the awkwardness. Okay. Here we go. So, yeah, I'm Jason Grant. I'm a manager with the forest team at WWF US. And I have been having some issues with my camera. And so I'm actually going to stop the video because I'm afraid it's going to glitch and be a distraction. But yeah, I have been active in this space of promoting responsible forestry, ecological forest products for pretty much my entire career, over 30 years now, and have been with WWF for the last 6 years. All right. Well, I'm going to start with a high-level definition of climate smart wood. Climate smart wood products, according to Climate Smart Wood Group, are those that are recycled, reclaimed, salvaged, or reused, or virgin wood products that come from or otherwise support climate smart forestry. And of course, this begs the question, what is climate smart forestry? Now, our understanding of climate smart forestry is that it's a spectrum or a continuum. So it's not like you go, it's climate dumb, whoop, climate smart, right? There isn't like this absolute black and white threshold. Climate smart forestry is about improving over baseline conventional practices, and there isn't a fixed endpoint. We are always learning and innovating, and our understanding of forestry, forest dynamics are going to evolve. And so climate smart forestry practices are going to evolve. But from a high level, we think that there are several key features that characterize climate smart forestry. So, one is mitigation. This relates to carbon sequestration and storage. One is adaptation. So, this is about the ecological integrity, diversity of forests, their ability to resist and be resilient in the face of climate change. There's a social and economic component of climate smart forestry, in our opinion. Local people need to have a stake in it in order for forestry to be sustainable. Indigenous people's rights should be respected. And then the last point, which I've already touched on, is that we think that climate smart forestry needs to reach beyond the legal minimum. And because the regulatory floor is uneven in different jurisdictions, what this implies is that what's climate smart in one place could be a lot less climate smart in another. So, for instance, California is known for having very stringent forest practice laws, Oregon less so. So, what's climate smart in Oregon could be less climate smart in California. What are some examples of climate smart forestry? One thing that's important to stress is that there simply is not one set of practices that work everywhere. There's a lot of different forest types. There are many different practices that can improve on the factors that I just mentioned that can mitigate and increase resilience. This is a handful of examples. Seth, in his presentation, will be elaborating on this, so I'm not going to dwell on it. It's a lot of words on the screen, but it'll give you a flavor. So, a few of the resources of the Climate Smart Wood Group I'd really like to highlight. Jen already mentioned our procurement guidance. There are four major sections to the procurement guidance. You can see them here. I'm just going to touch on them briefly. The first section is about advancing traceability and transparency in the forest products industry. Why is it important? Why is it complicated and actually hard? And what are strategies that folks who want to help drive, encourage traceability and transparency? What strategies can people pursue to try to advance that goal? So traceability is about tracking wood to or from the origin. Transparency is about disclosure of information, both about the supply chain and about the origin. The next major section are our recommended procurement options. We have three suggested ways to source climate smart wood currently. You see them here. We will add more options if they emerge. We want to put forward everything that we can think of, but today these are the three that we think are solid. I already mentioned recycled, reclaimed, salvaged, reused. I think that this is pretty non-controversial. There's a really exciting movement in the US right now to build an industry around trees salvaged from, say, city streets or orchards or parks. These are trees that are today chipped and commonly landfilled or turned into landscaping. That's something that we'll have a whole webinar dedicated to at some point. We've been reclaiming wood from buildings and existing structures for a while now. Of course, reusing wood products and using recycled content is a good thing. So this one's fairly straightforward. The second one's certified wood, and as many of you may be aware, there are several competing forest certification systems around the world. The main ones in the US are Forest Stewardship Council, or FSC, and the Sustainable Forestry Initiative, or SFI. And Climate Smart Wood Group's analysis is that today FSC's forest management standards most closely align to our definition, our understanding of climate smart forestry. But this isn't to say that other certification systems couldn't be certifying, recognizing really good forestry. We just think that FSC is the most reliable way to identify climate smart wood products that come from managed forests, and that for the other system, you might have to do a little bit more homework. Why isn't that advancing? All right. And then the third option is intentional sourcing of wood from climate smart forestry operations. And we kind of playfully allude to this sometime as the choose your own adventure option. And this option rests on the reality that there are a lot of folks out there who are doing really good forestry who aren't certified to any system. And there's a variety of reasons for that. And so what we're suggesting with this option is that if you're a project team that is looking for climate smart wood and you know of an operation out there that you think is doing a good job, and we would encourage you to assess it with our definitions and understandings of climate smart forestry in mind, then figure out how to get their wood on your project. And we provide a good deal of guidance on how to go about that so you're not on your own. But it does require more work and more commitment, a greater dedication of resources. People often ask us about the role of LCAs and EPDs, life cycle assessment and environmental product declarations, in sourcing, identifying climate smart wood. And the unfortunate fact is that today, LCAs and EPDs aren't necessarily all that helpful. And the reason for this is that current methods don't account for the changes in forest carbon stocks that can result from different approaches to forest management. And I'll be expanding on this quite a bit later in my presentation. Um, but for now, just suffice to say that the greenhouse gas portion of an LCA, the calculation portion rests on what's an assumption of what's called biogenic
Oh,
carbon neutrality.
Jason, I'm
Yes.
so sorry to interrupt. It seems like your slides are no longer advancing. We're seeing certified wood still.
Oh, you are?
And at least one attendee reported the same. So I think it's
Oh,
not just a glitch on my end.
okay. Well, thanks for telling me. That's strange because on my screen, I am not seeing that. So let me stop sharing and start sharing again.
Okay, thanks. Sorry to interrupt your flow.
No,
But
no,
LCA is the
not at
kind of thing
all.
that definitely deserves a diagram.
Okay. Can is it working now?
It doesn't appear to have changed.
No. Okay, I'm seeing a flag saying your screen sharing is paused.
Hmm. I
Could this be happening on your end?
think it needs to be stopped. There's a pause and stop are separate screen sharing buttons.
Okay. All right, I stopped. Shall I share
There
again?
you go. Yep.
Okay. All right. How about now?
Now you're good. And kudos, thank you for all the helpful audience members who are chiming
Yeah,
in on the
thanks.
Q&A.
Thanks, everybody. In the inevitable technological challenges, it seems like. All right. Well, as I was saying, there's this assumption of biogenic carbon neutrality, and basically it rests on the idea that overall in the US, forests are absorbing as much carbon as is being emitted, because where forests are managed across the entire average US, we have regrowth, we have replanting and regrowth that's in balance with timber harvest. But what that means is that if you're looking at a specific product that comes from a specific source, it just rests on this national average, and you don't get a picture of what's happening in that forest and how it could be managed in a way that is really building up a carbon surplus, if it's really climate smart forestry. Or it could be managed in a way where you're creating a carbon debt. And the LCA and EPD actually obscures that fact. It only reflects the emissions associated with what's downstream from what happens in the forest. So in the manufacturing and transportation of the product. And that can be greatly outweighed by what happens in the forest. So today we think that, of course, LCAs and EPDs, it's not that they don't have value, but when it comes to identifying wood from climate smart forestry, they're not very useful. Okay. All right, so now I'd like to take a step back and talk about wood as a potential climate solution. And I want to start by talking about carbon, focusing on carbon, because of course it's really central to the conversation about how wood use is relevant to climate change. So I think we all know that forests are key to confronting the climate crisis, and that's in no small part because they sequester and store vast quantities of carbon already. But it's also because they have the potential to mitigate global warming by drawing down a significant portion of the excess carbon that's now in the atmosphere. So trees, of course, absorb carbon dioxide, and through photosynthesis, they use the sunlight and convert the carbon into sugar, and that combines with other ingredients to make wood and grow the tree. The chemical composition of wood is about 50% carbon, and that carbon is, of course, going to remain safely socked away until the tree dies, or it's cut down and the wood rots or burns. So, this is why wood construction can be seen as a way of taking carbon out of the atmosphere and locking it away for the long term in wooden buildings. And it seems like common sense that substituting wood for concrete, steel, other relatively energy intensive materials used in construction would be an effective way to reduce net carbon emissions. And of course, there are many studies that back this up. But what too often gets left out of considerations of the potential benefits of wood is the impact of logging on forest carbon. And I've talked about this a bit already, but forest carbon is the carbon that's stored in the forest, and that includes what's above ground in live and dead trees and understory vegetation, as well as what's below ground in roots, fungi, soil, that sort of thing. Now, it's important to note that forest carbon stores are at their highest in primary forests, or what are colloquially referred to as old growth forests. And these are forests that are relatively undisturbed by human activity. So there's many different types of forests across the world. There's tropical forests, temperate forests, boreal forests, but across these forest types, generally speaking, the amount of carbon that you have in the vegetation and soils is pretty much maxed out when the ecosystem is in a climax state. Some of you may have heard the argument that mature forests are quote unquote decadent and that they stop absorbing carbon, so we should cut them down and plant new trees. And it's true that as forests age, emissions from tree mortality gradually increase until eventually, when the forest reaches that climax state, emissions and sequestration are more or less going to come into balance and the carbon stores are going to plateau. But when such a forest is logged, we lose a lot of that carbon in the atmosphere, and it will take a long time to reabsorb because trees don't grow all that fast. So what this means is it makes no sense to replace old forests with young managed forests. And doing this creates a carbon debt that can be really substantial, and that can only be recouped if those new trees are left alone for a long time. It could be hundreds of years. And of course, we don't generally do that when we're managing a forest for timber production. Another thing you'll sometimes hear is that young trees remove more carbon than old ones. But the fact is that small trees just don't sequester and store all that much carbon. While it's true that young trees grow faster than older ones, what really matters here isn't the rate of carbon removal, but rather the quantity. So a 5-year-old sapling grows fast, but it's so little that the amount of wood it adds every year and the amount of carbon it removes is comparatively small. Whereas the growth rate of an old tree is quite a bit slower than the sapling, but it's so much bigger that the lower growth rate translates into a larger amount of wood added and carbon stored. And in fact, there was a study that indicated that the biggest and oldest trees in forests around the world of all types stored fully half of the carbon in the forest, that the largest 1% of trees stored half the carbon. And it's also important to recognize that forest management impacts forest carbon stores at all scales, from individual trees to forest stands to entire managed landscapes. And that this results in near-term losses of forest carbon, even if reforestation occurs after timber harvest. So after trees are cut down and bucked into logs, a good deal of their stored carbon stays behind in the forest, and it's released in the relatively near term as the roots and branches and leaves and needles and other things that are left behind in the forest rot or are burned. More of the carbon is lost as the logs are processed into wood products, and the downfall from that processing may be burned to generate power, or it's going to rot somewhere and be released in the relatively near term. So the point is that there's only a portion of the carbon in a live tree that's carried through to the end product, and that carbon debt won't be recouped until a new tree reaches the same size as the one that was logged. When forest stands are logged, it also causes the release of carbon stored in soils as well as the understory vegetation. For those who aren't familiar with the term, in the context of forestry, a stand is a limited and distinct area that is subjected to a specific set of management techniques. And logging across large landscapes can also be a major source of net CO2 emissions, especially if more mature forests are replaced by tree farms where the new trees aren't allowed to grow to the same age as the forests that they replaced. And what this really boils down to is a question of the starting condition. It's a really critical variable. This chart shows two different starting conditions. So the dark green line is a stand of primary forest, and the light green line is an area where a stand of trees was planted. It's where afforestation is occurring. So here you can see that with the old growth, the level of forest carbon, it starts high, but it drops steeply when that forest is logged, while with the afforestation, it starts low, and then it builds up over the course of several decades. Now, the stand here is logged once every 40 years on a sustained yield basis, meaning that the tree growth and timber removals are in balance. And so you get to this wave pattern where the average level stays the same. So that you can see the forest carbon is dropping with each harvest and then it's building back up before the pattern repeats. But where the starting condition is old growth, the net carbon loss, again, the carbon debt is substantial, whereas with afforestation, you get this surplus. So It's relatively straightforward to visualize how forest management impacts forest carbon stores at the level of an individual stand, but the picture gets more complicated at the landscape level, where numerous stands are being managed simultaneously, which is pretty much almost always how it works in forest management. And I want to offer an analogy that helped me wrap my head around this. So picture the managed forest landscape as a bucket, and the forest carbon is the water inside it. So the landscape is made up of multiple stands that have been logged at different times and are in different stages of regrowth. Some are taking up carbon and some are releasing it. And the challenge is to determine how all of these offsetting inputs and outputs are affecting the overall carbon stores. And this is what we need to do to understand the differing effects of different approaches to forest management. So, as I noted, carbon stores are generally highest in primary forests. So, here you have a full bucket. And when the forest is logged, it impacts both the amount of water coming into the bucket and the amount leaking out, but the larger impact is on the leakiness. So the more holes you have and the bigger they are, the leakier the bucket. And the leakier the bucket, the less carbon it will store. In this analogy, each hole would represent a stand that's been logged, and the size of the holes is related to the intensity of the forest management system. The large clear cuts characteristic of conventional forestry in some timber producing regions can be pictured as larger leaks, and relatively frequent harvests can be pictured as more numerous ones. So, on the other hand, on the right, we see a bucket where there's less intensive and extensive logging, which can be pictured as smaller and less numerous leaks. And as the trees and stands across the managed forest landscape regrow after logging, the leaks are going to get smaller. And if too many leaks that are too big aren't created in other parts of the landscape, then overall, less water, less carbon will escape from the bucket, and the average level across the entire landscape will increase. So, in other words, if there's a transition from more intensive to less intensive, climate smarter forestry, you can increase carbon stores significantly even as you continue timber production. So again, a portion of the carbon stored in harvest trees is carried over into wood products, and it can be stored for decades in buildings or other long-lived applications. And this too is a carbon store that can increase over time if the number of wood buildings also grows. If there are reduced overall emissions as a result of substitution of wood for other materials, then this is a benefit that accumulates over time as well. But any gains could be lost if forest management results in significant net decreases in levels of forest carbon. And on the other hand, if the wood used in building construction comes from improved forestry practices that build up forest carbon, then any substitution benefits that exist will be enhanced. So I'm going to wrap up. Here's the main points I'd like to offer to you as takeaways. Really, the keys to realizing the potential of wood as a climate solution, but really realizing the potential as forests as a climate solution is conservation, restoration, and stewardship. Logging of the world's remaining intact primary forests should be minimized, and protections of those forests should be increased. Ecologically appropriate forest restoration and afforestation is a great idea and needs to happen at scale. And that means planting the right trees in the right places and creating the conditions for trees to survive and grow into forests. In some cases, these new forests could be protected. For example, when they create corridors between patches of primary forest, and in others, they can be managed as new sources for timber. And again, we should be striving to improve forest management so as to increase average levels of carbon storage and maintain or rebuild ecological integrity. And all this would not only improve the management of forest carbon, it would yield numerous other important environmental benefits, including less damage or improvements to wildlife habitat, greater ecological complexity and biological diversity, reduce negative impacts or improvements to soil and water quality. As it happens, what's better for carbon is nearly always better for all the other critical ecosystem values and services that forests provide. All right, I'm going to stop there. Thanks a lot for listening. And Seth, I think it's over to you.
All right. Thanks so much, Jason. Thanks for that introduction. While I'm starting my share here, I'll just say that my name is Seth Zuckerman. I'm the executive director at Northwest Natural Resource Group. We're a nonprofit based in Seattle, and we promote the benefits of ecological forestry and help people actually practice them on their land. Let's see. I'm hoping that you're seeing my slide.
Yes, looks good.
Oh, okay, great. So, and what I really want to build on here is some of the generalities that Jason was talking about, and bring it down to some of the specifics, because I'm coming to you today from Washington State, which is the second largest timber producing state in the U.S., second only to our neighbor Oregon, just the other side of the Columbia. And so I thought it might be useful to ground this conversation in some of the ways that timber gets to the forest, and then ultimately, since many of you are architects or otherwise in the building industry, how it gets to your projects. And so while we're starting this, I just want to ask Jen if you'd put up the poll that we talked about, because how forests are, the climate impact of forestry depends a lot on who owns the forest, because that also will affect then how those the values and the goals that are guiding the management of the forest. So you have a moment here to vote while I go through the next couple of slides. Today I'll be talking about a couple ways to be more climate informed in your management of forestry. One of them is mitigation, meaning ways of keeping more carbon out of the atmosphere where it will make mischief with the climate. And the second, which I'll spend a little bit less time, but is also very important, is on adaptation. How do you manage the forest in your care so that it will be more resilient as the climate changes? So we'll talk about both of those. And I think it's just key to recollect that whether it's chickens or lumber, sourcing matters. So this idea that, as Jason was saying, you can just look at an overall average of the ways that timber is produced and say, well, overall, it's a net zero impact on carbon. It ignores the more granular impacts. So I'll be talking about those as we go on. Let's close the poll and see what people thought. So which sector owns the most forest land? All right, well, we have, this is just a good example of why betting markets are not the best predictors of actuality. In fact, it is families who own the largest amount of forest land in the US. And the people who voted for government may say, well, Alaska, there's a lot of federal forests there, so perhaps you might be right in terms of the data set, but for the data set that we're working with here from Forest Land Statistics of the US and published by Butler and Sass in their US Forest Service publication a couple of years ago, families own about half the forests in the US. Corporate, meaning all, and not just corporations, but real estate and investment trusts and other vehicles for investing in forest land as an aggregate of investors own about a quarter, and the rest, as you can see, distributed among these different other government and public players. But then who actually cuts the timber? And this is a complicated graph, so I want to unpack it here sort of gradually and carefully. Let's start just by looking at the blue bars. And so even though corporate owners have only a quarter of the forest land, they represent the largest amount of timber harvest for a couple of reasons. Because timber is their business, they've chosen the most productive lands. And and because timber is their business, they're focusing on how they can produce the most from that land. Family owners they own the land for a variety of reasons. And so even though they have twice as much land as the corporate sector, they're producing just a little bit less. And then you can see kind of scattered amongst the other owners. Now, if we turn our attention to the red bits on this graph, that's how much is cut per acre on average per year. And you can see that the red bar here, bar and whiskers here for the corporate owners are the highest, again, both for the two reasons that I mentioned, and then for families, a lot lower, and then even lower still for state, local, other private and tribal, and finally, very low for federal for a variety of reasons having to do both with the complexity of the bureaucracy that it takes to harvest timber, as well as the fact that they're really trying to serve a multiplicity of needs with the public's forests. Now, these averages, once again, they hide, in the aggregate, they hide a very granular difference amongst the various states where different kinds of ownerships predominate. So you can see that family ownerships predominate in the Midwest and the Mid-Atlantic and part of the South, whereas here on the West Coast, where the timberland is so productive and where it's been a great source of investment returns, corporate owners predominate, and then federal owners in the Rockies, tribal owners play a big role in North Dakota and Arizona, and Minnesota has actually a lot of local forests and state forests where that's where a lot of the forest land is held. So I'm going to zoom in now from this sort of national look to talk about the business as usual case here in the Pacific Northwest, in one of the main timber baskets of the US, and look at the idea of climate smart forestry first in relation to the business as usual case. And so I feel like we have to start, because as Jason said, climate's not a binary choice of is something climate smart or climate dumb. Rather, there are gradations of climate smartness. And so we're going to start with the baseline of what is the climate smartness of the business as usual management of industrial forests. What we're seeing here is the typical way that forests are harvested in the Pacific Northwest, even aged on what's called a short rotation, meaning a relatively short interval between when the trees are planted and when they're harvested, and harvested in their entirety. And it's not just a single gap that's opened up, it's more like a Swiss cheese of gaps. So this here is a picture just to the west of Mount Rainier. That's the area, the snowy area here is Mount Rainier. And we're looking at a distance of roughly 8 miles end to end here. And so you can see that there's quite a bit of that the harvest in this satellite photo you can see has been quite intensive. And that's a function of ownership. If we overlay the ownership patterns over top of that, you can see that the more transparent area is primarily industrial ownership. This blue bit here is conservation ownership, owned by a community forest and a land trust. This green area directly south of the large block of clear cuts is state ownership, and then the purple is in state park. So if I go back, and go back and forth between these, you can kind of see the impact that ownership patterns, and therefore the values and goals of the owners, are having on the management of the forest. The consequence from the forest standpoint is that as a forest would normally develop from the seedlings on the left here in the shrub herb stage through pole and sapling and then young forest, it's right about at this boundary between young and mature forest where forests are typically cut and then reset back to zero. Let's think then about how that impacts carbon storage over time. We ran some numbers for a hypothetical plot of forest land in Lewis County, which is just south of Olympia, our state capital, some productive forest land. And what you see here is these 3 bits of pools where carbon can be stored. As you plant the trees, as we hypothesized in 1980, and then they would grow, that's the green bit, total stand carbon, meaning the carbon that's stored in the stand. And then there's a thinning at age 30. That's where you start to see some carbon wind up in the blue wedge. That's where carbon is being stored then in the built environment, in the studs of a house, for example, or the timbers of a bridge. And then as products pass through their life cycle, to the end of their life cycle, then you wind up in the red bit. As products get thrown away, then there's more carbon stored in the landfill. All of those pools are good places to keep carbon because it means from a mitigation standpoint that the carbon isn't in the air. Instead, it's fixed either in the built environment, in the forest, or in the landfill. And you can see from what each of these little sawtooth spikes represents is a single rotation. So every 40 years, they come back, they cut the trees. There's more, with each cutting, there's more wood stored in the products pool, and the forest regrows, and it's in what you might call a steady state. But there are other ways to get timber out of the forest, and this doesn't have to be the before and after. Instead, by selectively cutting the trees and allowing the trees to get to the remaining trees to get to an older age, you can get a harvest of timber and still allow the stand to continue developing along that continuum that I showed earlier. So here on the left side of the photo is a thinned part of the forest, and on the right side of the photo, a place where the forest is still dense and harvest hasn't yet happened in this cycle of cutting. We'll talk in a second about whether that is climate smarter and what the impacts that has on mitigation. To take a view from ground level, you can see, when I look at this forest, one of the things I see is not only how dense it is, how dark the forest is, how little understory there is, so very little growing in the forest except for the trees. So no shrubs, meaning less valuable wildlife habitat. And also, if you look up to the top, you'll see that the canopy, the live crown, or is starting to shrink, meaning the trees have shaded out one another's lower limbs, and so each one has just a little tuft of green to photosynthesize with and suck more carbon out of the air. Okay, and so one of the solutions that we help people put into practice is to thin the forest. These days, most of that sort of cutting is done in a mechanized fashion. This is a feller buncher, which is holding onto the tree, cutting it off at the base, and then laying it down in a pile to be dragged to the landing. Here at the landing, the trees are processed. This is one of a couple different systems. There's also systems where the trees are manufactured into logs right there in the woods in what's called a cut-to-length system. Either way, when we're talking about forest thinning, we're not talking about hippies with draft horses. We're talking about mechanized equipment that is cutting these trees and processing them both more safely for people because the workers, because they're encased in steel cages instead of standing next to the tree with chainsaws, but also in a more efficient fashion. We're going to look here at what that's a little bit of a time lapse of what that can look like. This is one of those stands at the just to the west of Mount Rainier at the Nisqually Community Forest that we help to manage. You can keep your eye on the tall tree in the center that's not painted to be cut, and also at the little blue spot in the lower left as sort of anchors as we look at what happens from the before to the after. And you can see we're still looking at a forested environment as the stand has the ability to keep developing, even as the stumps in the foreground show that, yes, there's been material hauled away to turn into products to house people and make chairs and window frames and so on. So how does this compare with the modeled fate of carbon that we looked at before? This was the previous graph with a 40-year rotation. And then when we modeled an 80-year rotation with each of these little points on the graph is a thinning where the amount of forest stand carbon has gone down, but the amount of wood in the product pool has gone up. You can see that over time, there's an increase in carbon that's kept out of the air as both the amount of forest carbon is greater, that's the green, and the blue, the forest product pool, is greater. Now, why is that? If you think about it just from a biophysical standpoint, here's a picture of a forest that has been cut and recently replanted. The whole mechanism that we're trying to foster here to pull carbon out of the air and sequester it in forests is photosynthesis. And for the first 5 or 10 years, until these trees close their canopies between them and are able to and really get into their fast growth phase, there are a lot of photons that are going to waste. All the photons that are falling between the trees are failing to help with photosynthesis, whereas with the other picture we just saw, they are captured more efficiently and they're running that photosynthetic cycle forward. What does this mean from the standpoint of the investor and actual timber harvest? Here's the business as usual 40-year rotation on the left and an 80-year rotation on the right. You can see more stand carbon, more tons on average stored over, we used a 100-year period here for the analysis, more tons stored per acre in all the different pools of carbon, as well as more timber yield. And interestingly, what I heard from a privately held family in forest company, Port Blakely, recently at a conference, is that they are often operating not on a 40 or an 80-year rotation, but a 60-year rotation in between. And they find that two 60-year rotations produces 20% more wood than 3 40-year rotations. And those are not modeled values, but actual values. And I find that really reassuring because, of course, as they say, all models are wrong, some models are useful. So to have some actual grounded data is really helpful. I wanted to, in the last couple of slides that I have, turn my attention to the other side of the mountains. A lot of our work is done on the west side, which any of you are familiar with the Pacific Northwest know it's the wetter side and has a different set of forest ecosystems. Whereas, and just to give you an example of what that means, we just had a string of 13 dry days and people were starting to get worried about a drought right here in the middle of our rainy season. Not such an uncommon phenomenon on the east side. And so in a different forest ecosystem, you would imagine that you would support different densities of trees. This is a picture on the east side, courtesy of Vaughan Brothers, who work in northeastern Washington. And what looks like would be a great for a density of forest here if it were something I spotted here in our neighborhood, not so good on the east side because they exist in a different fire regime. So the natural state, if you will, based on weather, on soils, on forest types and on, well, on climate, dryness, heat, availability of lightning and other ignition sources is that they would have a high frequency of low severity fire, whereas we're accustomed on our side of the mountains to a low frequency of high severity fire. So when they look at this, they realize that it's a forest that needs to be thinned even more drastically than we would, and then it would need to be underburned in order to reduce the amount of biomass, because for them, fire is fuel limited more than it is ignition limited. And then ultimately, at the end of the day, it would look a lot sparser than what we would consider to be a healthy forest on our side of the mountains. But after thinning and burning, a landscape that's much more resilient to the more frequent fires that they can expect, and that will become even more frequent as the climate continues to change. So with that, I'm going to sort of tee up the next webinar where we'll talk about what happens to to logs after they head to the mill, and talk about how to get wood from climate smart forestry into your projects. And just thanks very much for your attention. Feel free to check out both our website and our book written by me and my colleague, A Forest of Your Own, which talks in much more detail about how to produce these kind of, how to practice ecological forestry. And I'll hand it back over to Jennifer to moderate us for a set of questions.
Excellent. Thanks to you both. We've got a number of really interesting questions that have rolled in. We might not have time for all of them. So as a reminder to the audience, you can upvote questions. So if there's one you're particularly interested in hearing the answer to, feel free to use that function. That'll help us narrow it down. But I thought maybe we would start first with the question that came in from Susan about asking, what's the control metric for comparing carbon sequestration old versus young trees? Is that about the amount of biomass or how much acreage? And so it sounds like maybe Jason or either one of you could take that question, maybe just reiterating that the differentiation between sequestration and storage, and how young versus old trees are kind of optimizing for one versus the other.
Sure. So
go ahead, Seth.
Yeah. So in this conversation, or in climate forestry conversations, people talk about storage as the amount at any given time that exists on the forest or any of these other pools where carbon can be stored, whereas sequestration is the rate at which carbon is being pumped from the air into the biome. And I think that the best metric to use would be tons per acre per year of carbon that is being sequestered and pulled out of the air on net. Obviously, there's some decay that happens as dead branches or if trees die and decay. So you want to look at the net amount of tons per acre. A lot of times people focus on the percentage, and that's where they get very excited about the high percentages growth rates that a forest might manifest when it's quite young. But per acre, at least in our region, it peaks between 40 and 100 years.
Thanks, that's great. And also, I guess there's a couple of clarification questions for you, Seth, on some of the data that you showed. So maybe I'll just lump those together real quick, just because folks might be wondering. One was about how the different land ownership types are classified. Like someone was asking whether Weyerhaeuser, are they a family owner? It's a family company, but I would imagine they're in the corporate category, but wondering if you know what the cutoff is for family ownerships versus corporate in those data sets.
Yeah, I think that will certainly any ownership that includes the ownership of a mill would be considered an industrial or corporate ownership, regardless of whether it's owned by a family. I mean, Sierra Pacific is also a family-held company, but that would also definitely be in the corporate category. A lot of times in other data sets, you'll see them talking about non-industrial private forests versus industrial private forests.
Okay, great. That's a helpful clarification. There's a lot of nuance, even in those big categories. And then one more for you, Seth. In the graph that you were showing, the 80-year rotation with carbon storage, someone was asking, do we assume that 80 years there's a clear cut? Or kind of what
So,
happens after the graph
right,
ends?
right. For simplicity, we modeled, yes, there would be a clear cut at 80 years, but there's actually no reason you would have to do that. You could continue, depending on, again, your goals, values, and objectives, you could continue thinning. And there's actually some thinning trials that started back in the 1950s in the Oregon Coast Range that suggest that this idea of the productivity of a site culminating at a certain point, that you could extend that for quite a long time, like into the past a century, just by continuing to thin at the appropriate rates.
Yeah. Well, one more for you, Seth, and then I'll toss one to you, Jason, or if you have one, because I think you can see all the questions that you're really burning to answer, um, was about the sizes of trees. So obviously for folks, we've got folks from all over. In different regions, this will be different, but it's Seth, in your neck of the woods, those trees in the longer rotations, like how big are they? With the person noting that mills usually require the butt end of logs to be less than 24 inches for processing. So does that create a limitation?
Well, I think if you look back, I think that the processing infrastructure that exists is a function of the supply that's available. If you looked 40 years ago, then there are mills that would only process larger diameter trees. And so to the end, in our region, there still are mills that will process large trees, large logs. So that I don't see that as a limitation. It's more of a build it and they will come sort of situation where, to the extent that there would be more supply, then there would be infrastructure would arise to deal with that. You can make a much greater diversity of products from a 32-inch or 36-inch tree than you can from an 8 or 10-inch tree.
Mhm. Great. Well, there's another question that's gotten 3 votes, so I'll toss this one out there to either one of you, I guess. But Brooke was saying that I'm aware but not super knowledgeable about various efforts to incorporate changes in forest carbon stocks into the accounting of what EPDs. Maybe this is for you, Jason, because you teed up the EPD topic. Does Climate Work Group support or advocate for any of those? Any commentary about how that's incorporated?
Yeah, absolutely. We would love to see changes in forest carbon stocks and specific ownerships carried over into products that are sourcing timber from those sources. This is sort of a Rosetta Stone that I think many of us are seeking. We have had long-term collaborations with some of the leaders working on those methodologies, but they're just not mature. So as soon as we feel like we have something that's ready for prime time, then we'll be trying to promote it and really bring it to as wide an audience as we can.
If any of you have contacts at Underwriters Labs, there's talk of revising the product category rule that says that all wood is considered to be carbon neutral that comes from the US. And actually, so I think that would be a good thing to constitute an advisory group to look into.
Yeah, that's a good plug. And we're just coming up to the top of the hour. There's so many good questions. And thanks those of you who are using the chat to share your resources and information as well. That's wonderful. We can try to follow up with some of you individually, but that's just to follow off what Seth said. That's a great plug for if you are interested in these type of topics and getting into the weeds. The Climate Work Group is a great organization to join because these are the kind of conversations and things we get into as a group, and it's easy to form little work groups and dig in and find like-minded folks who want to volunteer to advance some of this work. So I'm going to stop us there just for the sake of time and do my little closeout spiel for all of you, which is just to note that I'm not even going to share a slide. I'll just remind, thank you again to Seth and Jason for being our speakers. That was a really informative presentation. Thank you all for joining. We had a really great crowd here, a really, really excellent turnout. And, just to remind you all, you remember that slide, if you can picture it in your head, the different ways to get involved. climatesmartwood.net can donate, come to the webinars. If you really are jazzed about the webinars, you want to share it with your network. We have, graphics and things. You can help promote them in your company newsletters or whatever makes sense for you. You can just reach out. And then just a reminder that next month's webinar will be, again, the last Wednesday of the month, February 25th at noon Pacific, 3 Eastern. And the topic is going to be on the guidance document that was referenced, specifically on the traceability and transparency part of that. So if that's of interest, be sure to sign up on the website and we will look forward to seeing you there. Thanks all.